To be doing some wave physics. We're going to be studying the physics of waves. We can firstly we can start with the definition of a wave. And a wave, I could write the definition right here. A wave is a disturbance, that propagates that propagates in a medium. So normally, when you have waves, some waves do have a medium, right? You can have, like, most waves do have mediums, like, water waves, their medium is water, or sound waves, their medium is air. Sometimes you can have, like, there's no medium. Electromagnetic waves can travel in a vacuum. But the idea is that the disturbance is a disturbance that propagates in a medium. It's not the medium. There's a disturbance in the medium, and that propagates the disturbance itself, not the matter, right? So you don't have matter moving, so you have to get out the idea, the myth that the matter is moving, that matter is equal to wave. So it's not the matter that moves, it is the disturbance that propagates matter. So this is a myth. So that means that no, the wave is the disturbance. And so we could see some examples, right? The string doesn't move along the string. If you have a string and then, like, you really make it move, it's not the string that is moving, but it is the disturbance itself on the string. So what travels in a wave, the wave carries. So what travels in a wave will be energy, momentum, and information. So this is the basic core of what is a wave, of waves. So firstly, we could talk about traveling waves. So the main equation for the main canonical equation that we'll use is this one: y x of t will be equal to a sin of kx minus omega t plus the phase constant. So here, a will be our maximum displacement, so how tall the wave is. This is just as always, just as we did in simple harmonic motion. This is the max displacement, the amplitude, the how tall the wave is. So when you see a wave, you could see how tall it is. This will be a, like that. K here is a constant, which is 2 pi over lambda, which is the wavelength. Omega will be 2 pi f, 2 pi times the frequency. And so basically, the k will tell us how fast the phase will change in space. This will tell us how fast the phase will change in time. So basically, so when it's minus, so when we have minus here, it tells us that the shape, the wave, will be moving to the right. But when it's plus, the shape will be moving to the left. So this is the core part of the equation that really tells us how the wave is displacing through space and time, and where and what its displacement, what the meaning is, what its physical meaning is going to be. It could tell you if it's right or left, and it could tell you exactly what if it's in space or in time. A very important equation that we will have will be the wave speed. So wave speed, I will write it right here. Wave speed will be v is equal to lambda over t, so the wavelength divided by the period, which you could also write as this because of our core equation of that the frequency is the inverse of the period. So you know that the wave speed is the wavelength divided by the period. So we can have some key ideas we could get from here. The is that the medium is essential. We can know the v is very essential. The speed will depend on the medium. The medium itself will set the wave speed, right? If you have string tension or the density, or if it's air or water or a vacuum, it will that the medium that itself will set the wave speed. And so once v is fixed, you can choose one of the wavelength or the frequency. So the amplitude, what's important to know is that the amplitude does not affect the speed. It is only the wavelength and the frequency that will essentially decide the wave speed. Another thing that will be important for us will be the snapshot versus history graphs, which I'm not sure if I'm going to draw on this whiteboard, but maybe it is important to talk about because these are essential when doing wave physics. So we'll have two types of of slides of two graphs we'll have, and that is snapshot and history graphs. So we have to distinguish for this because there can be a lot of exam traps when you do this. So a snapshot graph will be y versus x at a fixed time. So this could be a distance or displacement. It's right. So it is a snapshot. It is on y or x, and it's trying to show wavelength, and it is at a fixed time. Whereas a history graph, it is a y t at a fixed position. So as we can see, the difference is that at a history graph we have a fixed position, and here we have a fixed time. I'm going to write it fixed time. Hence, that's why it's not on the graph, right? So here, on this one, the time is not on the graph in a snapshot, but in a history graph, the position, which is x, is on the graph. We do have distance or displacement, but we do not have position. Then, so that means that instead of the wavelength, this will show the period and frequency, and here this will show the wavelength. So it's important to realize that snapshots will show the wavelength and the history graph will show the period and frequency, whereas this is fixed position and time will be on the graph, and this will be fixed time and position will be on the graph. So another thing to know is energy and power on a string, in string which can do some waves. So we have both kinetic and potential energy per wavelength. So we could derive this, and we could see that because energy is conserved, we could see that kinetic energy of a wavelength will be equal to the potential energy of a wavelength. That will be equal to this equation. This is a constant. The amplitude squared times the omega squared angular frequency times the wavelength divided by 4. So this will be a very essential equation that we can use to find out the kinetic and potential energy due to them being conserved. So this will be really important. So both of these are equal, and you could derive from both. And there's not a lot to say about this equation because you mainly have to know by heart. You have you have your constant here, and you have, if you have your amplitude and angular frequency and kinetic wavelength, you can know what the kinetic or potential energy of your system is. If you don't, you can derive mainly. If you have a problem, you can mainly derive these things. So there's not a lot to say about this. And the total energy, will basically be the same. It's just that instead of divided by 4, we'll have divided by 2. So let's rewrite this. It's basically the same, but this time it's divided by 2. And so this is the energy. And if we remember, we could also have power. The average power will be, if we remember what power is, it is joules over time. It is energy or work over time. So how much work someone can do over time. So it'll be 1/2 mu times a squared times v. So it's basically same thing here. It's just that we get v because the wavelength divided by t will give us the speed, basically. So very important thing that the very essential thing that we need to know here is that energy is directly proportional to amplitude squared and to frequency squared. So these are the two things that are very important to take away in the energy part. So when we think about energy, this is the most important thing that we think about. So then we could also talk about reflection and transmission. So when a wave will hit a boundary, the frequency will always stay the same, but the speed changes. So essentially, when we have a boundary, so when wave hits boundary, let me just hits boundary, say like it hits like this. One thing that's very important to know is that frequency stays the same, so is same, but the speed will change. Speed changes, and because of that, so will the wavelength change. So we could define, therefore, reflectivity as PR over PI, and we can define transmissivity as PT over PI. So therefore we can also know that the reflectivity plus the transmittivity will be equal to 1. So this is the most important equation. These are the three equations that are the most important for this part, for reflectivity and transmittivity. And finally, the final thing that we will talk about here, or maybe, I'm not sure if this is the final thing, but maybe I will add a couple of things after this, but this will be pretty important to talk about. It is the most important of all of wave physics. This is the equation for wave physics, which is very important to understand. And this is the wave equation. This is literally how it's called. It's called the wave equation. And so the wave equation says basically this. It's a differential equation which is equal, so the double differential equation be equal to y over x will be equal, will be I have a brown pen. will be equal to 1 over v squared, and then derivative of the change in y or change t. So as we could see here, because as we saw before, we saw two types of graphs. We saw a snapshot with y and x, which basically we have it in this part of this equation at the left of the equation. We could see that it is a variance of the position from the displacement, and here we could see the variation of the displacement by the time, which is basically like speed, but we have speed here. So we could interpret this as a spatial curvature that will cause acceleration, and this equation is a linear differential equation. So superposition holds. So this is much of things about wave physics. It is really important to know some basics about wave physics. Hope this was helpful. We saw some equations like we saw the definition of a wave, which is a disturbance that propagates in a medium. We saw this equation, right, of a displacement of a wave. We saw the wave speed. We saw this is very important for exam, the snapshot versus history graph. We saw some energy equations. We saw resistivity and transmissivity. And finally, we saw wave equation, the partial differential equation that describes how disturbances like sound, light, or water waves propagate through space and time, and how it relates, and how this relates, very, very important, let me write it, how this relates to the acceleration of a wave. This is the acceleration of a wave, and how it relates to its curvature. Just to clearly write that here. So the spatial curvature of a wave really is related to the acceleration. Well, that's about it. I hope this was helpful for some wave physics.